Welcome back. Today we're going to talk about multivariate linear systems and row operations. Really, that's a fancy way of saying we're going to find solutions to systems of equations with multiple variables, not just two, but three or four maybe. And then we're going to talk about row operations, which means how are we arranging these things in matrices and then moving them around. First of all, we want to look at what does it mean to solve a system. Well, solving a system means finding all of the variables, finding the values for all the variables. So solve the system. Find values, and in this case it's x, y, and z for x, y, and z. Well, conveniently, check it out what we've got here. We already have a z equals 3. This example is going to lead us into our next examples. But what we're going to do is we're going to do a process. Because we have this, we can put it back in. We're going to use back substitution. Okay, and back substitution is basically just saying something, I already know what z is, so I can just substitute it back in every equation. Well, it doesn't particularly help me to sub it into the first one because I'd still have two variables. But if I sub it into this second line, and you're going to start to hear us talk about rows and lines, the second row, it's actually going to help me because then I'll have y minus 2 times 3 equals negative 7. Well, that's really convenient because now I have y minus 6 equals negative 7, and I can add 6. And I have y is equal to negative 1. So now I'm going to use back substitution again to back substitute both of those into the first one. And so I'm going to take x minus 2 times negative 1 plus 3 equals 7. So I used back substitution and back substitution. So x plus 2 plus 3 equals 7. So I'll subtract 5 from this side. And I've got x is equal to 2. So what does my answer look like? It's an ordered triple because it's not an ordered pair. There's three variables, and it goes x, y, z. That's all there is to it. So I'm going to use back substitution. Well, Gaussian elimination, which is our next section, is going to help us get to a situation, a scenario where we can back substitute. And so here's what it's going to look like. We'll start with a matrix, which comes from a set of linear equations that have x's and y's and z's, maybe w's, 4 or 5 variables sometimes. And we're going to try to get it into a form where we have our last line equal to a variable. And so there's a couple of steps associated with it. And there's a couple of things we can do. What we can do. And it's kind of a puzzle because we're going to do these things to get to the point where we have one variable that we can start to back substitute. So the first thing we can do is we can interchange two rows. So I could switch them around to get one on the very bottom that's going to be more like, z equals 3 like we had in the first example. Number two, what we can do is we can multiply or divide one equation by a non-zero number. Okay, and that could be useful. Like let's say we had 2z equals 6 here. We could divide it by 2 and we'd have z equals 3. The third thing that we can do is we can add a multiple. So add a multiple of one equation to any other. And before you start to think, well, I don't really know what that means, I'm just writing it down. The process that we're actually going to be doing is elimination, except we have 3 equations. So I'm just going to put in parentheses elimination. Okay, so we're going to be doing elimination with two equations at a time. Let's look at an example. To solve this system, we want to get it into what's called triangular form. And before you're like, what does that mean? Check it out up here. This is the triangular form here. Check it out. Okay, because I end up on the bottom with a variable equal to a number. In the second line, the second row, second to last row, I have 2 variables. One of them is shared with the bottom one. And in the top line, and it goes up and up and up and up, So I can back substitute. In this case, it's z equals 3. Then I have a y and a z. Then I have an x, y, and a z. So it builds on itself. And so triangular form is going to have last row is a variable equals a number. The second to last row, two variables, and one of them is the same as the last row. That's very important. Like in this equation up here, I had z equals 3, and in my second to last row, I had one of them was z. That's why back substitution worked. Two variables, and my third last row, three variables, okay, and up and up and up. Okay, and so it's going to keep going up and up from there. But this is going to be our basic framework for what we're going to do here. So how do we do it? How do we get to this point? Well, some things that we can do. We want to try to eliminate one variable from two rows first. And it's going to be the same variable. So what I'm going to try to do is I'm going to try to eliminate my x in these two rows here. See, I've got an x here, and that's really useful because I could say, to eliminate x from the second row, I can multiply it by -3. So what I'm going to do is I'm going to multiply row 1. So I'm going to do -3 times row 1, and I'm going to add it to row 2. This is the notation. So -3 times row 1, add it to row 2. That's what this notation means. So what does it look like? Well, if I do -3 times row 1 and add it to row 2, I'm going to have -3x plus 6y minus 3z equals -21. That's what I'm going to be adding to my second row. So my first line actually doesn't change. First line doesn't change. My second line now becomes, I add this to it, so I have 0x, and then I'm going to have plus y, and then I'm going to have, so this is -3z minus 2z.
Jason Smith, please come to the high school office. Jason Smith.
And that's going to be equal to -7, because -21 plus 14 is -7. My last line has not changed yet. 2x minus 2y minus z equals 3. Okay, so I eliminated x from that one. Now, remember, I'm trying to get to this triangular form. So what's stopping me right now? Well, I kind of see, I got to cut out this x. And so what I'm going to do is -2 times row 1, and I'm going to add it to row 3. Why would I do that? Well, that's going to help eliminate my x here. So I'm just systematically eliminating variables. And so -2 times row 1 is going to be -2x plus 4y minus 2z equals -14. Okay, that's what I'm adding. My top line doesn't change. X minus 2y plus z equals 7. And then I've got, and I don't have to write this again, y minus 2z equals -7. When I add -2x, so this would be 0x, and then 2y, and then minus 3z equals, and this is going to be -11. Okay, so that's what I end up with here. Now, I've systematically eliminated my x variable. Well, what do I need to do now? Now, I need to try to get into my triangular form. And so now I'm going to try to eliminate this variable here. I want to get rid of this one because that's going to leave me with just a z in the last line, which is what I want. So I can back substitute. And the way to do that is you look at this line here. I've got this solo y, and I'm going to do -2 times r2 plus r3. I'm trying to eliminate a variable from that last line. So what's it look like? Here we go. -2 times r1 would be -2y. Plus 4z equals 14. That's what I'm adding. So my top line stays the same. I'm pointing to the screen like you can see that. x minus 2y plus z equals 7. My second line doesn't change. Y minus 2z equals negative 7. And now when I add this to my bottom line, I have 0y, and then 4z plus negative 3z would be z equals 3. Check it out. Now I have my triangular form that I wanted. Why does this help me? Because now I can back substitute. Okay, and so y minus 2 times 3 equals negative 7. You're going to see this is the same example. We just had a different form of it. And so if I add 6, then y is equal to negative 1. If I back substitute into the first equation, I've got x minus 2 times negative 1, because that was y. And then plus 3 equals 7, so x is equal to 2. So my ordered triple is 2, negative 1, 3. Same example as before, except it was a different form. That's how this Gaussian elimination goes. I try to eliminate one variable from 2 rows first, and then eliminate a variable from the bottom, so I'm left with one single variable in triangular form. All right, so in this one, I'm going to solve this system. I'm going to try to get into that triangular form so that all I have to do is do back substitution. And so I'm looking for opportunities to eliminate the same variable from 2 lines. Well, if I look here, I've got this x up here. This is really nice. So what I'm going to do is I'm going to do row 1, row 1 plus row 2. That's going to eliminate an x. So on top I'm going to have x minus 3y plus z equals 4. And then when I add that, I'm going to have 0x. Negative 3 plus 2y would be minus y. And I'm going to have z minus 5z, so minus 4z equals 4 plus 3 is equal to 7. Last line stays the same, 5x minus 13y plus 13z equals 8. Okay, got to eliminate x from that bottom row. Very convenient to have this x here, because now I can do negative 5 times row 1 and add that to row 3. When I do that, negative 5x plus 5x would be, oh, so here, let's rewrite x minus 3y. Very important to keep track of everything as you do it, because you're going through these steps, and you want to have these lines where all your totals are staying the same time to time, because we're trying to keep track of it all. So negative 5x plus 5x would be 0x. I'm going to leave that spot blank. Negative 5 times negative 3y would be 15y plus 13. Negative 13y would be 2y. Negative 5z plus 13z would be plus 8z. And then I'm going to have negative 20, because it's negative 5 times 4. Negative 20 plus 8 would be negative 12. So let's see what we got here. We can eliminate some variable. So now I'm going to try to eliminate one of these variables down here, so I'm left with just one variable in the bottom row. So what I'm going to do is I'm going to do 2 times row 2 plus row 3. Okay, and if I do that, I still have my top line, x minus 3y plus z equals 4, and this one stays the same, minus y, minus 4, minus, no, minus 4z equals 7. And then if I do 2 times row 2, that's going to be negative 2y, so this is 0y, and then this would be 2, so negative 8z, so this would be 0z, and this would be 14 plus negative 12 is equal to 2. So I'm left with x minus 3y plus z equals 4, and negative y minus 4z equals 7. And then 0 equals 2. Okay, so sometimes we get this situation here where we get a last line that's nonsensical. Well, you guys know from previous that if we get a line that's nonsensical, we would say that this system has no solution. So once you've proven that you did everything correctly, and you can go back and you can check it on your, you can always check it on your math and those kinds of things by doing back substitution or whatever it happens to be. If the last line doesn't make sense, 0 equals 2, then we have something where it's no solution. Okay? All right, so let's talk about some forms here. Row operations and row echelon form. Row echelon form is a variation of this triangular form. But to do it, we're really going to work with just a part of these equations. Because essentially, are we really working with the variables? No, we're not really working with the variables. We've been working with the coefficients. And so an augmented matrix just takes out the coefficients. And answers. So for this system, I can use a matrix by saying I'm just going to take the coefficients. So on this part, I'm going to use the coefficients. And I'm going to go like this. 1, -2, 1. 3, -5, 1. 2, -2, -1. And I'm also going to use the answers. So 7, 14, 13. See? Check that out. Okay? 3. Should be 3, not 13. And so 1, -2, 1, 7. 3, -5, 1, 14. 2, -2, -1, 3. Those are the coefficients of all of these and the answers of these. Okay? So that's what this looks like. So the coefficient matrix, what does the coefficient matrix look like? The coefficient matrix is literally just the coefficients, not any of the answers, just the coefficients. So the coefficient matrix is just 1, -2, 1, 3, -5, 1, 2, -2, -1. And that's the coefficient matrix. That's all there is to it. We're going to use these instead of carrying these equations down and down and down and writing all these variables, because essentially all we're concerned with is the coefficients. And so what are we going to do? We're going to talk about row echelon form. Okay, and row echelon form is going to be a form where we have a bunch of zeros and a bunch of ones. Okay, so we'll talk about row echelon form and reduced row echelon form. But row echelon form looks kind of like this. We're going to take this previous equation and we're going to work with it a little bit. So I'm going to take this coefficient matrix, 1, -2, 1, 7, and 3, -5, 1, 14, and 2, -2, -1, 3. And we're going to start to do a little bit of solving here. So what we're going to do is we're going to do the same process as triangular form, same process as Gaussian elimination on this matrix. So here we go. Same notation here. I'm going to take and try to eliminate this number here, because it's going to be ones and zeros, because all those coefficients become 0. You see that? And so I'm going to do -3 times row 1 and add it to row 2. And what do I get? Well, what I get is, and actually with this, I can do more than one at once. So I'm also going to do -2 row 1 and add it to row 2. So see how I can start to kind of combine these things instead of having a step and a step and a step. First one. Leave row 1, because we didn't do anything to it. When I do -3 row 1 and add it to row 2, I end up with a 0 here. Important to keep them now. -3 times -2 would be 6, plus -5 would be 1. -3 times 1 plus 1 would be -2. And -3 times 7 would be -21, plus 14 would be -7. I'm also going to do this process simultaneously. -2 times row 1 plus this one would be 0. -2 times -2 would be 4. 4 plus -2 would be 2. -2 times 1 would be -2. -2 plus -1 is -3. And -2 times 7 is -14. Plus 3 would be -11. Okay, so see what I've already done there? In one step, I eliminated those variables. Now, I'm going to try to get rid of this one here, right? Because I'm going to get myself into a situation where I have 3 variables. 1, 2, 3, because this is my answer column. Second row is 2 variables. Third row is 1 variable. So what do I need to do? I'm going to go -2 row 2 and then add that to row 3, right? So here we go. 1, negative 2, 1, 7, 0, 1, negative 2, negative 7. And then when I multiply row 2 by negative 2, I'm going to have negative 2 plus 2 would be, so this is 0. Now this is 0, and negative 2 times negative 2 would be 4. 4 plus negative 3 would be 1, and then negative 2 times negative 7 would be 14. 14 plus negative 11 is 3. So essentially, what do I have here? Essentially what I have is z equals 3, and then I can back substitute and back substitute, okay? So row echelon form, what is it? Basically, it's triangular form in Gaussian elimination. And so, what's it look like? Well, it's got to be zeros here, right? It's got to be zeros. It's all zeros underneath there. And then my leading coefficients are 1s, okay? So the lead coefficients are 1s, okay? So that's row echelon form. So what does it mean for us? So let's look at solving the system using matrices. And what we're going to try to do is we are going to try to get into reduced row echelon form. Okay, reduced row echelon form looks like this. We're gonna end up with as many rows as there are variables. So in this case, we've got 3. So I'm gonna have 3 rows, and I want to have something that looks like this. Let's just put in a number 2, something like this. So 0, 1, 0, 3, 0, 0, 1, 4. Let's just keep it like that. And what I'm looking for in reduced row echelon form is I'm trying to get all 1s, because this means x equals 2. This is y equals 3. This is z equals 4. There's not a whole lot of work there to be done once I get done doing all of my row operations. And so I want 1s on the diagonal, and I want to get zeros underneath and zeros above as much as possible. When it's reduced row echelon form, it's going to have this element of I've made the attempt to get all zeros underneath that diagonal of 1s. 1, 1 for every single variable. And I've made an attempt to get zeros above. Now sometimes what's going to happen is you're going to have a random 3 stuck in here, something like that, which we'll see in this example. But we're trying to eliminate as many things that aren't my 1s on my diagonal as possible. So let's look at this. This set of equations has an augmented matrix. It looks like this: 1, 1, 1, 3, 2, 1, 4, 8, 1, 2, negative 1, 1. Again, what do I want? I want 1s on my diagonal. I'm pretty close there. I just got to do a little bit of elimination. I'm trying to get zeros here, 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 and here. Answer's obviously happening there. Well, how am I going to do that? Well, my first line is pretty good for right now. So I'm going to do a couple things at one time. I'm going to take negative 2 times row 1, and I'm going to add that to row 2. That's going to eliminate this. And like we said before with triangulation, what we're trying to do is we're trying to eliminate the x's first, and then a y from the third row, et cetera, et cetera. So I'm actually triangular form, reduced row echelon form, they go hand in hand, but one's a more advanced process. So that's the first thing I'm going to do. That helps me eliminate this one right here. I'm also going to take negative row 1, and I'm going to add it to row 3. To remind myself where I'm putting these things, this sum is going to go in row 2, this sum is going to go in row 3. I did 2 things at once, so let's see what shakes out. 1, 1, 1, 3. Negative 2 times row 1, negative 2 plus 2 would be 0. Negative 2 plus 1 would be negative 1. Negative 2 plus 4 would be 2. And negative 6 plus 8 would be 2. I'm also going to take negative times row 1, so negative 1 plus 1 would be 0. Negative 1 plus 2 would be 1. Negative 1 plus negative 1 would be negative 2. And negative 3, so negative 3 plus 1 would be negative 2. Check out what I got here. This is good. So I've taken care of this 0 and this 0. So now I'm going to work on this one. I want to work on the underside first, then the upper side. So I see here I've got negative 1 and a 1. So what I'm going to do is row 2 plus row 3, and I'm going to stick that in row 3. Top row stays the same, 1, 1, 1, 3. 0, negative 1, 2, 2. Add those two together, I got 0. I got 0. I got 0. I got, uh-oh. I end up with all zeros in the bottom row. Well, let's just keep going, because after all, I'm trying to get ones here. So what I'm going to do is I'm just going to keep going, because now I have zeros in the bottom row. That's actually a good thing. It's actually a special case that we're going to look at here. But we're going to keep going and try to get zeros still. So I have a 0 here now. That's good. I want to try to get zeros in these three top spots here. So I see an opportunity to get rid of this one. I can add row 2 plus row 1. So I'm going to go row 2 plus row 1. To remind myself, I'm sticking that in row 1. So 0 plus 1 is 1. Negative 1 plus 1 is 0. 2 plus 1 is 3. And 2 plus 3 is 5. Okay. My second line, and actually what I can do is I know I need a 1 here, so I'm going to do negative row 2. I'm just going to multiply it by a negative 1. So I've got 0 and 1 and negative 2 and negative 2 and zeros on my bottom row. Well, check it out now. What do I have? I have a situation where, yeah, I could try to eliminate this 3, but anything I add, like if I manipulate row 2 to eliminate this 3, that's going to add something here because it's already a 0. And so what this is called is I can't do anything more. I can't get a 0 here. I can't get a 0 here. So this is reduced row echelon form. Well, what does it tell me? On the bottom line, this is z. What does z equal? Well, when 0 equals 0, that's an infinite number of solutions for z. And so my solution looks like this. Z just is, because the last line says 0 equals 0, so anything can go in for z. But what you'll notice here is this is x plus 3z equals 5. And this is y minus 2z equals negative 2. I'm running out of space. Well, I got to figure out what that means. So I'm going to come over here and I'm going to say x plus 3z equals 5. And y minus 2z equals negative 2. And so x is equal to 5 minus 3z. And y is equal to negative 2 plus 2z. Everything is defined in terms of z. And so my y is negative 2 plus 2z. My x is 5 minus 3z. This is infinite solutions. Because anything could go in for z, and then x and y are both defined. This is an okay situation, but it comes about because I have all zeros in the bottom row. All zeros in the bottom row tells me infinite numbers of solutions. Okay? So that's how that works, guys. You can go ahead and try the next one, and what you're going to find is you should end up with it with infinite finite solutions as well. Okay, so try that one. That should be your answer when you get done. Thanks for watching, and we'll see you next time.